So we're going to be looking at oxidation-reduction reactions, otherwise known as redox reactions. Basically, an oxidation-reduction reaction is one in which electrons are transferred from one reactant to another. And basically, what ends up happening is you undergo two processes. You have an oxidation process and a reduction process. The oxidation process is the loss of an electron by a substance, while the reduction is the gain of an electron by a substance. So oxidation, or that process of those losing electrons, has been something that has been viewed from the perspective of oxygen being the substance that reacts with a metal in order to produce oxidation. However, what needs to be understood is that that does not only occur between metals and oxygen. There's other oxidation reduction processes, but basically this nomenclature, this oxidation nomenclature, comes from reactions in which oxygen react with a specific metal. Now, you guys have seen these in textbooks and everything else, but the fact that the copper is this nice green color on the Statue of Liberty, or rusting of your bike and tarnishing, things of that sort. Those are all examples of oxidation processes that occur when specific substances, specifically metals, are in the presence of oxygen. So oxidation reduction processes are things that we see regularly, we inherently understand in terms of a visual cue that something has changed. We have chemical changes. However, understanding what's physically happening between our reactants is what we need to glean from this lesson. So if we think about this from the perspective of reactivity, we want to think about the valence electrons that are being used in these processes. So we know that calcium has 2 valence electrons, while oxygen has 6 valence electrons. So in order for either of these elements to be able to form their octet or to be in their most stable states, they're either going to be losing or gaining electrons. And you know, they can do this by sharing, they can do this by electron transfer. In this situation, because we're dealing with metals and nonmetals coming together, it's typically going to be that electron transfer process. So calcium, we know, is one of the metals. Metals like to give up their electrons. In this case, we have 2 extra. So if we lose 2 electrons, we end up with the calcium 2+ ion. Same thing here, same concept. If we gain these 2 electrons from that calcium, our oxygen is now going to have its octet and be a 2- ion. These two come together and give you your calcium oxide product. So what you guys have to understand is that the transfer of electrons is not electrons coming from, you know, outer space or the middle of nowhere. The reality of it is that the electrons are coming from each of the reactants and being accepted by the reactants that are present in that specific reaction. So electrons are not coming from nowhere. They're basically being exchanged between your reactants that are involved. Now, please remember that oxidation reduction reactions can occur in different scenarios and different situations. It doesn't just have to be this metal-oxygen construct that we have here. However, it allows us to very easily see how this process actually works. So, in order to identify if we have a redox reaction or oxidation reduction reaction, we have to have a bookkeeping method that facilitates that type of tracking. We have to be able to see if we have actually undergone oxidation and reduction from reactants to products. And in order to do this, we've basically created a bookkeeping method. And what we do in this method is we assign something called oxidation numbers. And these numbers allow us to visualize and see if we have undergone this electron transfer process. So there's a series of rules here that we're going to discuss and basically utilize to assign these oxidation numbers. So rule number 1, for any monoatomic ion, the oxidation number is always equal to the charge of the ion. Okay, so the charge on an ion is actually the literal physical charge. There's a certain number of electrons present, there's a certain number of protons present, and that interrelationship gives us our charge associated with the ion. So in this situation, Na plus is an example here. It's lost an electron, so it's formed a +1 charge. Okay, so the oxidation number, the bookkeeping method we use, is going to match that physical charge that is present on that ion. Same thing here with the sulfur ion. If it's a 2- charge, the oxidation number is 2. Now, oxygen, in this case, 2- charge is what's present on that ion. So the oxidation number for that specific example will be 2-. Now, if we look at other examples of oxygen ions, there are a few that make it where it's not 2-. There are some exceptions to that rule, and we'll see those a little bit later in this lecture. Okay, rule number 2, for any atom in its elemental form, so basically its natural state, the oxidation number is always going to be equal to 0. So right here we have 2 examples of diatomic molecules. We have H2 and O2. Hydrogen and oxygen gas both occur as diatomic molecules in nature. So their oxidation number, because they're in their elemental form, is going to be 0. Same thing here with this phosphorus molecule. It also forms a or has a oxidation number that's equal to 0 because P4 is its elemental form. Okay, same thing would be true for sodium metal or copper metal, or basically any other metal or substance that's occurring in their elemental state. All 3 of these examples here would all have oxidation numbers that are equal to 0. So the bookkeeping method, if it's in its elemental form, its natural state, the oxidation number is 0. Now, number 3 here is basically just a general statement. Generally speaking, most of the time, nonmetals are going to have negative oxidation numbers. So just file that in your memory as you're going through these types of problems. Okay, number 4. Oxygen is usually going to have a -2 charge. Okay, that's normally what we see. However, if we're looking at oxygen in compounds called peroxides, okay, the charge on the oxygen or the oxidation number is going to be -1. The reason why is because this 2- charge on this peroxide ion is actually spread amongst 2 atoms of oxygen. So each one of those oxygens has a -1 charge. So basically your oxidation numbers, although they generally follow a very clear and direct rules, sometimes there's exceptions, and you need to make sure that you're monitoring those exceptions and having them in the back of your mind. So as we continue to look at some additional rules, okay, hydrogen, okay, so hydrogen, it is a nonmetal. However, its oxidation number is usually +1. And it's usually +1 when it's bonded to nonmetals. And it's -1 when it's bonded to metals. Now, typically we see hydrogen bonded to nonmetals in most of the reactions that we look at. However, there are examples where we will be looking at hydrides, as they're called, when metals are attached to the hydrogen molecule, and that would give us a -1 oxidation number. Number 6, fluorine always has an oxidation number of -1. The other halogens should theoretically also have that same oxidation number. However, this is not true when the other halogens are bound to oxygen. Okay, their oxidation numbers will actually be positive in that situation. So fluorine, it follows the rules. It's always going to have an oxidation number of -1. A lot of the other halogens will also have a -1 oxidation number. However, when those other halogens are bound to oxygen, they'll end up having a positive oxidation number. Now, the last rule in terms of assigning oxidation numbers is that the sum of all the oxidation numbers in a molecule must equal the overall charge of the molecule. So what do I mean by this? Okay, well, if I look at a generic example, NaCl, sodium chloride, okay, this is an ionic compound. I know it's made up of 2 ions. I know it's made of sodium +1 and chloride ion -1. Okay, now sodium chloride, I know that when it comes together, basically there's a neutral substance there. Okay, there's no charge out here. So what that means is that the oxidation number on my sodium plus the oxidation on my chlorine should give me an overall number of 0. And in this case, +1 plus a -1 is going to give me 0. So the overall oxidation number values are going to be equal to the charge of this molecule. Since this molecule is uncharged, we would expect the 2 oxidation numbers to equal 0 when summed together. So this is just the basic set of rules. We're going to go ahead and practice on the next slide, and then we're going to see where this becomes an applicable, useful tool in terms of identifying oxidation and reduction reactions. Okay, so let's go ahead and let's look at this example right here. Na2O, so sodium oxide. Okay, sodium oxide is an ionic compound. I know in this situation that I have sodium. Okay, and sodium has a +1 charge. Oxygen, this is not the peroxide situation, so O2 minus is what I have there. Okay, please notice though that I have 2 sodiums. Okay, so I have 2 +1 oxidation numbers. Yes. Okay, plus the 2 minus oxidation number here. So that gives me an overall oxidation number of 0 in terms of their sum. So how would I label this? I would label this as +1. I would label this as -2 in terms of oxidation numbers. Okay, and basically this is how I would do my labeling. Same thing here. Okay, hydrogen, remember we said it's +1 unless it's attached to metals. Sulfur is not a metal, so sulfur is not going to be changing the oxidation number setup for hydrogen. Sulfur in this case is a -2 in terms of oxidation number. I know this because I have 2 positively 1 charged hydrogens. If I sum the 2 together, I have 2 + 1 oxidation numbers plus a -2. That gives me an overall 0. So the next example is a little bit more complicated. Potassium in this case, we do know that it's +1 because potassium ions form +1 charge. Okay. In this situation, though, we have a polyatomic ion. Now, the charge on this polyatomic ion is 2 minus. The reason why I know that is 1, because I've memorized it off my list, and also because I have 2 +1 charged potassium ions present. So in order to figure out the oxidation numbers associated with the sulfur and the oxygen, I must basically break that off as its individual pieces and then subsequently assign to each individual atom. So the way I would approach this is basically first look at the one that I know. So oxygen in this case, this is not peroxide, right? This is just oxygen atoms in a molecule. So oxygen typically has a -2 charge, right? So I have a -2 charge coming from each of the oxygens present. Each oxygen present is going to contribute to the overall charge of the molecule, right? So -2 times 3 is going to give me -6 coming from the oxygens. Now, -6 is what's coming from the oxygens, and this sulfur subsequently has to have a charge that's going to balance the -6 coming from the oxygens and still maintain a -2 charge coming from the overall molecule. So what am I going to do? I'm just going to do a little bookkeeping down here for my own personal bookkeeping system. Okay, so oxygen is contributing -6. Okay, I need a -2 charge, so I'm going to need a +4 here on the sulfur. Okay, 4 minus 6, right, is going to give me overall -2, so that makes sense. So my sulfur is going to have a +4 charge, and each individual oxygen is going to have a -2. So if I bring this back to the original molecule, okay, I have a +1, I have a +4, okay, and I have a -2. And if I look at this with respect to the overall charge, if I look at the K2SO3 molecule, I notice that there's no charge there. And if I look here and I count up all my pieces, I have 2 potassiums with a +1 oxidation number, plus 1 sulfur with a +4 oxidation number. That gives me a total of +6. Oxygen here, there's 3 of them. Each one has a -2. So 3 times -2 gives me -6. +6 plus -6 is going to give me an overall oxidation value of 0, which matches what I see here. So basically there's some bookkeeping involved here. What I want you guys to make sure that you're paying attention to is that you are not putting the total contribution from all 3 of the oxygens up here. Okay, so each one of these oxygens is a -2 in terms of oxidation number. So you're not putting the -6 up here, you're putting -2. Same thing here for potassium. I have 2 potassiums. Each one of them is a +1 charge. It's not +2 as in the total charge coming from both K2 or potassium atoms. Okay, so paying attention to that detail will help alleviate some of the problems some of you might run into. Okay, so we can do the same example down here with a sulfate ion. Okay, same thought process what we saw up above. In this case, though, we don't have to worry about the potassium situation. Okay, so we're going to look at oxygen, right? Oxygen normally has a -2 charge, right? This is not an example of a peroxide. So what we're going to do is oxygen has a -2. 2 times 4 is -8, right? Okay, the overall charge of this ion is -2. So I have to have a charge on my sulfur that balances the -8 that's coming from the oxygen, but continues to keep the overall charge of the molecule. So 2 minus is what I need. So +6 is what we're going to have here as our oxidation number, because +6 minus 8 is going to give me -2. So in terms of assigning oxidation numbers, we're going to have +6 for our sulfur and -2 for our oxygen. And the sum of those with respect to the individual atoms present gives you an overall oxidation number that is a -2. Okay, so guys, this is the basic approach to assigning oxidation numbers. Being able to assign these numbers is something you want to practice, you want to get involved in, because it's necessary for you to be able to do the next step. So the tools that we just learned are going to allow us to look at different reactions and decide if they are oxidation reduction processes. And the way that we're going to do that is by first initially assigning oxidation numbers to everything on both of the reactants and product side. So what we're going to start with is first we're going to identify all the oxidation numbers on our reactant side. So sodium, this is a metal, so it's in its natural state, so oxidation number is 0. Same thing here with chlorine. Oxidation number of 0 because chlorine's a diatomic. Okay, sodium chloride is a compound. It's an ionic compound, and we know that sodium forms a +1 ion, so the oxidation number is going to match that charge. So our oxidation number here is +1, and our oxidation number here for chloride is -1. So what we're going to do is we're going to look at both of these, both the reactants and product side, and we're going to decide if oxidation reduction has occurred. So if we look at sodium, it has an oxidation number of 0 on its reactant side and a oxidation number of +1 on the product side. That implies that the sodium has lost an electron. Okay, so oxidation has occurred. If we look at the chlorine example, chlorine has gone from an oxidation number of 0 to -1, so it has gained 1 electron. So it has been reduced. So this is a redox reaction. Okay, we know this because of that change, and we can actually identify what is oxidation and what is reduction. So the sodium lost an electron, so oxidation has occurred, and the chlorine gained an electron, so reduction occurred. So we can identify the portions and components that either gain or lose electrons in this specific example. So if we look at this next example here, we have potassium iodide and lead nitrate reacting to form lead iodide and potassium nitrate. And we want to decide, hey, is this a redox reaction? Okay, so what we're going to go ahead and do is we're going to assign those oxidation numbers. Okay, so potassium iodide, potassium is a ion in an ionic compound. Potassium forms +1 charges, so the oxidation number is going to be +1 as well. Iodide is -1 in this situation. Okay, so the lead ions in this case, in the lead nitrate molecule here, NO3 nitrate is normally -1. There's 2 of them present. So lead's going to have an oxidation number of +2 because the ion is +2 charge. If we go to the right-hand side and we look at the lead on the reactant side, the same thing is true on this side. Iodide is normally -1 charge. There's 2 of those there. So our lead is going to be +2 charge. Okay, so we see that on both sides. Potassium on this right-hand side is +1. We would expect that as seen before because it's part of a ionic compound, because NO3 minus or nitrate is negatively charged, -1 charge. So that makes sense in terms of that specific molecule. Now I'm skipping over the nitrates because I want to point something out. Okay, please notice that nitrate shows up on both sides of the equation, and nitrogen and oxygen, which are the component sources for nitrogen and oxygen in this reaction, do not show up in any of the other products. So basically, nitrate stays nitrate on both the reactants and product side. It doesn't contribute to any new molecules on the product side. So we can treat these as not really having changed. However, I am going to show the bookkeeping just so you can see that there is no change there. But in the future, normally you can save yourself some time by ignoring them. So if we go ahead and we look at the example, oxygen normally forms a -2 charge. There's 3 of them. That's -6. Remember, nitrate has a -1 charge, right? So if I have -6 coming from the oxygens, then I'm going to need a +5 coming from this nitrogen. So the oxidation number on this nitrogen is +5, and it's -2 on the oxygen. Same thing over here, +5 and -2. As you can see, that's a bit of a redundancy and a time sink. However, it's good to practice for right now. Okay, so let's go ahead and let's look at our reactants and products. So potassium has a +1 charge on the reactant side, same charge or same oxidation number on the right-hand side, so it subsequently has not changed. Iodine on the right and the left, same charge, no change. Lead on the right and the left, no change. Same thing's true here. Same thing's true for the nitrogen, same thing's true for the oxygen. So the reality of it is that this reaction right here that we just looked at is not a redox reaction. Okay, there is no change of oxidation states for any of the molecules or atoms in any of the molecules. There is no increase or decrease or transfer of electrons. So the example you have here is not a redox reaction. It's not an oxidation reduction reaction. Okay, so questions like this come up. The way you want to approach it is first you want to assign oxidation numbers. Okay, and then you want to compare those oxidation numbers between your reactants and products. Okay? If there's a change, if you've identified all the oxidation numbers correctly, and if there is a change, you have a redox reaction. If no oxidation numbers have changed, it's not a redox reaction. So that identification process is the simplest approach. As I said, there are sometimes some shortcuts you can take. However, I suggest you doing it out the long way for the first few and then working your way into cutting the shortcuts.